Hello and welcome to our Multimedia Applications in Virtual Reality course. This section is dedicated to modeling the virtual world.
Interaction with virtual world depends on its perception. To perceive a virtual world, the user needs something to be rendered on their device. But before rendering can happen, that world must first exist in digital form, as a structured representation of all its objects, spaces, and interactions.
A valid virtual world model must satisfy several constraints to ensure realism, coherence, and immersion. Geometric consistency. Objects have realistic shape, size, and proportions. Spatial coherence. Positions, distances, and orientations respect physical logic. Physical plausibility. Interactions follow basic physical rules: gravity, collision, and resistance. Temporal continuity. Object movements and transformations are smooth and consistent over time. Semantic consistency. Each object's meaning and function are preserved in context. Computational efficiency. The model must be optimized for real-time rendering performance. When these constraints are respected, the user perceives the virtual world as credible and can become immersed in it.
The visual model forms the foundation of any virtual world. Other modalities, sound and haptics, are added on top to enrich user perception. Constructing the visual model typically involves 4 key stages. 1. Geometric modeling defines the shape and structure of objects and spaces. It uses mathematical representations, meshes, surfaces, volumes, to describe geometry. 2. Kinematic modeling defines movement and transformations, translation, rotation, scaling, that affect objects over time. This step introduces animation and user-object motion. 3. Topological modeling defines spatial relationships between objects, adjacency, connectivity, inclusion. It ensures spatial continuity, for example, doors connected to rooms, walls enclosing spaces. 4. Semantic modeling defines behavioral and interaction rules, collisions, interferences, logical relations, and user interactions. It gives meaning to actions. What happens when the user touches, moves, or manipulates an object? Moving on to a fundamental question, one that determines the choice of both format and modeling approach. What types of objects can exist in a virtual world? First, we have rigid and non-deformable solids. These are objects that do not deform. They only undergo rigid transformations, such as translation, rotation, or scaling. They represent static or mechanical elements like buildings, furniture, or vehicles. This class remains essential today, as it forms the basis for geometry, physics, and collision handling. They are typically modeled using polygonal or mesh-based techniques combined with rigid body physics. Next come the articulated solids. These consist of rigid parts connected by joints, allowing rotation, sliding, or hierarchical motion. They're used to represent mechanical or biological systems, such as robots, doors, or animated avatars. This type remains crucial in animation and kinematics, relying on skeletal modeling techniques, forward and inverse kinematics, and joint constraints. Then we move to deformable solids. These are objects capable of changing their shape or volume according to physical or procedural deformation laws. They are common in organic modeling for skin, muscles, fabric, or vegetation. They are absolutely vital for realism and typically modeled using soft body physics, finite element methods, or blend shape animation, where vertex deformation brings subtle movement to life. The fourth category is non-solids, or continuous media. This includes all matter without a fixed shape or volume, such as fluids, gases, fire, smoke, or particle systems. They help simulate dynamic natural environments and visual effects. These models remain fully relevant today, enhanced by GPU-based simulations, fluid dynamics, and volumetric rendering techniques. Finally, a more recent category, abstract or procedural entities. These are not physical objects, but logical, interactive, or data-driven entities. Holograms, force fields, user interface elements, or even AI agents. They play a growing role in XR and data visualization. This emerging class bridges the gap between modeling and interaction, using procedural generation and event-driven logic to create responsive, intelligent virtual elements.
The representation of geometric objects in a virtual world follows two main approaches, the primitive-based approach and the analytical approach. Each has distinct principles, advantages, and limitations. The primitive-based representation models objects using basic geometric components, such as vertices, edges, facets, and faces. It closely mirrors the structure of real-world objects and provides a direct, intuitive representation of shapes and surfaces. However, while it accurately reflects the physical nature of objects, it can be storage-intensive, requiring a large amount of data to describe complex models. The analytical representation describes objects mathematically rather than by discrete primitives. They include parametric forms, such as Bezier curves or NURBS surfaces, defined by mathematical parameters. Non-parametric forms, which may be explicit, for example, z equals f of x, y, or implicit, e.g., f of x, y, z equals 0. These representations are space-efficient and precise, making them ideal for mathematical operations and smooth surfaces. However, they are often less natural for modeling real-world structures and can be more difficult to implement in interactive or dynamic simulations.
Now let's take a look at this comparative table. It summarizes the two main families of geometric representations: geometric or primitive-based and analytical. In the geometric representation, the structure can be vertex-based, edge-based, or face-based. When we model with vertices or edges, access to higher-order elements like surfaces is limited. We need to define them explicitly. However, when we move to a face-based representation, access becomes direct, which greatly simplifies rendering and manipulation. In terms of resolution, geometric representations are limited by the number of discrete elements, except when interpolation is used to smooth surfaces. And computationally, their processing cost varies. For vertex or edge-based models, the complexity is proportional to the number of elements. That's O of n. For face-based models, it's often constant time, O of 1, since faces are already defined explicitly. In contrast, the analytical representation works with mathematical definitions. A parametric representation, like Bezier or NURBS, defines geometry through equations, allowing infinite and continuous resolution. Non-parametric analytical forms, whether implicit or explicit, offer direct access to geometric information, again with a constant processing cost, O of 1. In summary, geometric representations are intuitive and directly manipulative, but depend on discrete data. Analytical representations are mathematically elegant and precise, offering perfect continuity, but they're often more complex to compute and visualize interactively.